Have you ever thought about how cool it would be to write some really complex code in a language you already know, like C, and then just shrink it down into this tiny, powerful payload you can inject right into another program? Well, buckle up, because that's exactly what we're diving into today. We're going to look at this incredible shortcut, a method from the researcher Hazera Zaid that lets you do just that.
I mean, it's one of the biggest questions in cybersecurity, right? How in the world does some piece of malicious code actually run inside a totally normal program, say your web browser or some random system service? The answer? Well, it all comes down to a very special kind of payload, one that's built from the ground up to survive in a really hostile environment.
And yeah, that payload has a name, Shellcode. Now, the two words you really got to latch onto here are standalone and position independent. Seriously, think of it like a tiny, self-contained survival pod made of code. It doesn't need some big formal loader to get it started. It doesn't care where it ends up in memory. Its whole job is to just wake up and run. And that right there is why it's the absolute favorite tool for exploit developers and malware authors.
Okay, so if this stuff is so powerful, why isn't everyone writing it? Well, here's the catch. The old school way, the traditional way, you have to write it by hand, in pure assembly. And let me tell you, that is an absolute nightmare. It is so tedious, it's unbelievably hard to debug, and if you make one tiny mistake, boom, you're right back at the beginning. There's just gotta be a better way, right?
And there is. But before we get to that amazing shortcut, we really need to get our heads around the rules of the game. We can call them the Shellcode survival rules. These are the basic, unbreakable laws that make Shellcode completely different from a regular program you just compile and run.
So this table here just lays it all out perfectly. Think of a normal program, a PE file, like a big office building. It depends on the city's infrastructure, right? The Windows loader comes in, sets up the electricity, the plumbing, connecting it to all the system libraries. But Shellcode? Nah, that's our survival pod. It has to bring its own power, its own water, everything it could possibly need, all packed into one tiny space. It's got to figure out how to work all by itself.
And that brings us to survival rule number 1. It absolutely must be position-independent code, or PIC for short. See, a regular program kind of expects to be loaded at a certain address in memory. Shellcode? It has no idea where it's going to end up. It could be anywhere. So that means all of its logic, every jump, every time it grabs a piece of data, has to be relative. It's like instead of saying go to 123 Main Street, it has to say go 3 blocks down and take a right. It only knows where things are in relation to itself. And as if that wasn't already hard enough, the second survival rule is even bigger. A normal program has something called an import table. It's basically a shopping list. It hands it to the Windows loader and says, hey, I'm going to need these functions from these system libraries. Shellcode gets nothing. It's dropped into a process completely blind. It has to figure out how to find every single system function it needs, all on its own. So how does a piece of code that's totally blind find its way around the maze of a running process? Well, this is where things get really, really clever. It uses a classic genius-level technique called the PEB lookup. All right, let's trace this out. The whole journey starts at something called the thread environment block, or TEB. Every single thread running in a process has one of these. And here's the key. A special processor register, it's FS on 32-bit, GS on 64-bit, is always pointing right to the current thread's TEB. It's the one thing our shellcode can count on, a guaranteed starting point.
Okay, so from there, we take the next step. Tucked away inside that TEB, at a specific, known spot, there's a pointer. And that pointer, it leads us to the mother load, the process environment block, or PEB. This thing is a gold mine. It holds a ton of critical info about the entire process that our shellcode is now a part of.
And deep inside that PEB, we find what we're looking for, the treasure map. It's a special list, a linked list, called the in-memory order module list. And what's on this list? Oh, just an entry for every single DLL loaded into the process's memory. This is how we find our way. So let's break it down. It's a 5-step mission. Step 1, grab the TEB address from that special segment register. Step 2, follow the pointer from the TEB to get to the PEB. Step 3, walk through that module list until you find a key library, usually kernel32.dll. Step 4, once you find it, you parse its list of functions it exports to find the addresses of 2 golden functions, load library A and get proc address. And now the final step, number 5. Once you have those two, you've got the keys to the kingdom. You can load any other library and get the address of any function you want. Just like that, our shellcode isn't blind anymore. Okay, so that's the theory. Super cool, right? But now for the practice. Let's see how we use all of this to build an amazing method for turning regular C code into working shellcode.
The whole idea here is actually pretty simple, but it's really powerful. So on the left, that's your normal compilation. C code goes in, it gets compiled and linked, and you don't really see the messy bits in between. But on the right, that's our method. We basically tell the C compiler, look, do all the heavy lifting of turning my C into machine instructions, but stop. Before you make the final file, just spit out the human-readable assembly code. We're basically hijacking the compilation process right in the middle.
And here's the full recipe, the complete 7-step plan. First, you set up your C project, but you gotta follow some special rules. Second, you rewrite your code to use that PEB lookup we just talked about for all of its system calls. Third, you compile the C code, but you tell it to output an assembly file. Fourth, and this is super important, you manually edit that assembly file to make sure it's position independent. Fifth, you compile that tweaked assembly file. Six, you link it all together so you can have a test program. And finally, the last step, number 7, you just take that file and dump the raw code section. That binary blob you're left with, that's it. That's your shellcode. Now, before you even think about assembly, your C code has to be just right. These rules are absolutely non-negotiable. First, all your function calls to the system have to be handled with the PEB lookup. No cheating. Second, no global variables. None. Everything has to live on the stack. Third, you want to stay away from really long switch statements because the compiler can sometimes create jump tables that aren't position independent. And last, any strings you use have to be set up so they can be stuck right into the code later on. And this right here, this is the magic command that kicks the whole thing off. Using the regular Visual Studio C compiler, nothing fancy. The really important parts are /fa, which just tells it, hey, give me an assembly file, and /gs-, which turns off some security checks on the stack. We have to do that because those checks rely on outside help, and remember, our shellcode has to be 100% self-sufficient. So once the compiler spits out that assembly file, we have one last super important manual step. You see, a normal program keeps its code in one place, the .text section, and its data, like strings, in another place, the .data section. For our shellcode, we need to go into that assembly file and manually move everything from the data section right into the code section. That's how we guarantee our final payload is one single, unbroken block of executable code. So you might be thinking, okay, that sounds like a bit of work. Why do all that? Why not just suffer through writing it all in assembly? Well, let's talk about why this hybrid method is just so much better. It's really the best of both worlds. It's that simple. You get to write all the hard, complex logic in C, a language you already know and are comfortable with. You completely avoid the absolute headache of writing and debugging tons of assembly by hand. But, and this is the beautiful part, you still get that assembly file at the end. So you have total control to go in and tweak it, optimize it, whatever you want. Plus, being able to build a real, testable program first just makes the whole development process so much easier. The researcher who came up with this, Shiraz, really said it best. We don't lose the advantages of handcrafting the shellcode, yet we skip the tedious part. And that's what it's all about, right? Working smarter, not harder, to get an incredibly powerful result. So when you put it all together, what does this method give you? It's the power to take really complex logic, written in a high-level language, and turn it into something that's totally portable, totally injectable, ready to run inside almost any process out there. And that really just leaves one big question. What would you build with that kind of power?